So now we'll discuss some applications of the Maxwell's thermodynamic relation. So the first application of Maxwell's thermodynamic relation is this. We can use the relations to obtain the expression for Clausius-Clapeyron equation. So what is Clausius-Clapeyron equation? So it is the equation which gives us the rate at which vapor pressure must change with temperature so that two phases can coexist. Okay. So suppose we have two phases, one vapor phase and one liquid phase of some substance. They are in equilibrium with each other so that they are coexisting. Okay. So the two phases of one substance, suppose the liquid phase and the vapor phase, are suppose they are kept in a cylinder and they are in equilibrium so that they are coexisting. Okay. So and the pressure of the vapor is called the vapor pressure. So this equation will give us how can we change the vapor pressure with temperature, that is we change the temperature of the system and you observe that how the vapor pressure is changing with it. Okay. So we get the rate at which the vapor pressure is changing with the temperature. Okay. So that rate will be given by the Clausius-Clapeyron equation, which will tell us that the rate has to be in such a way that the liquid and the vapor will still be in equilibrium and they will coexist. Okay. So the required rate at which the vapor pressure must change with temperature so that the two phases can coexist will be given by this Clausius-Clapeyron equation. So let us start with the Maxwell's relation. So using Maxwell's thermodynamic relation, so we will use the first thermodynamic relation. Okay, you don't need to mention that it is the first relation. You can just write it is the Maxwell thermodynamic relation, the first one, which is del S del V at constant temperature T is equal to del P del T at constant V. Okay. Now if we multiply both the sides by T, we have T del S del V constant T is equal to T del P del T at constant V. Okay, so it is multiplying both the sides by T. Now you see, we know dq equals to TdS for an infinitesimal reversible process. Therefore, del Q in terms of partial derivative, del Q equals to T del S. Okay. So, you see in this equation, we can replace this T del S by del Q. Okay. So we can replace this T del S by del Q. So thus we'll have del Q del V at constant T equal to T del P del V at constant V. Okay. So suppose this is our equation 1. Okay. So this is equation 1. Now suppose let us imagine a cylinder which contains a liquid in equilibrium with some of its vapor. Okay, so here as you can see we have this cylinder. So this is the liquid. So this is the liquid and there is the vapor of this liquid. Okay, they are in equilibrium with each other and they are coexisting. Okay, so these two phases coexisting. So in equilibrium means there will be no further evaporation of this liquid. Okay, there is no evaporation of the liquid, so there is no decrease in amount of the liquid and increase in amount of the vapor. They have the they are the fixed amount. Okay, and that's why they are in equilibrium. Okay, so this area, this space which is filled with vapor has the maximum amount of vapor. Okay, because as there these two phases, this liquid and its vapor in equilibrium and they are in coexistence, this space which is filled with vapor is saturated with the vapor. That is, this space is holding the maximum amount of vapor it can hold. Okay, so that's why the pressure of this vapor is called the saturated vapor pressure. Okay, and this saturated vapor pressure is a function of temperature only. Okay, so let's just say that the pressure of this vapor is P. Okay, and both the vapor and the liquid are at same temperature T. Okay, they are at the same temperature T, and P is the pressure of this vapor. Now let us increase the volume. Okay, so now let us increase the volume of the system. Okay, so if we increase the volume of the system, here you see we have increased the volume of the system, then what will happen? Some of the liquid will convert to vapor. So there will be a phase transition, okay, from liquid to vapor. So if we increase the volume by keeping the temperature constant at T, then what will happen? Some of the liquid will convert to vapor. There will be evaporation. So now you see the amount of liquid has decreased and the amount of vapor has increased. But as the temperature is constant, we have not changed the temperature, we have only increased the volume, then what will happen? The vapor pressure will also remain constant, because we have already mentioned that the saturated vapor pressure is a function of temperature only. Okay, it does not depend what amount of liquid or what amount of vapor is inside the system. Okay, so even though amount of vapor has increased and amount of liquid has decreased, there will be no change in vapor pressure P, because it is function of temperature only and now the temperature is kept constant. So in this way, if we keep on increasing the volume, suppose we increase the volume even further, okay, then what will happen? More and more amount of liquid will convert to convert to vapor. But as the temperature is fixed constant, we are increasing the volume, keeping the temperature constant. Then the vapor pressure P will also remain constant. Okay. So now we can say that now if we allow the system to expand. So here you see, according to this diagram, we have allowed the system to expand. Okay, the volume of the system, the total volume of the system has increased at constant temperature. During this expansion, we have kept the temperature constant. Then what will happen? Then some liquid will evaporate to fill the extra space with vapor. Then some of the liquid will convert to vapor and fill the extra space. That is, due to the increase in volume, some extra space is created. That amount of space will be filled with the vapor. okay, which is vapor. Okay, so but the vapor pressure will remain constant. Okay, but vapor pressure will remain constant because we have kept the temperature constant, and temperature being a function and vapor pressure being a function of temperature only, it will also remain constant. So now let's say some liquid, so during this expansion some liquid of mass dm evaporates to vapor of mass dm. So the amount of liquid which evaporates to vapor is, suppose they have a mass dm. Okay, so some liquid of mass dm evaporates to vapor of mass dm by absorbing delta Q amount of heat. Okay, so this amount of heat delta Q will be absorbed from the atmosphere. Okay, now if L is the latent heat of evaporation per unit mass, then what amount of so what will be value of delta Q? So delta Q will be L into dm. Why? You see, L is the latent heat of evaporation for unit mass. So as this denotes the conversion of liquid to vapor, as this denotes a phase transition, so the amount of heat absorbed during this process will be the latent heat. Okay, so and it will be the latent heat of evaporation. Okay, per unit mass. Okay, so if the heat absorbed by unit mass of liquid to convert to vapor is L, because L is the latent heat of evaporation per unit mass. So we can say that the amount of heat absorbed for unit mass of liquid to convert to vapor is L. Okay, so the amount of heat absorbed by unit mass of liquid to convert to vapor is L. And how much? What amount of liquid we have? We have liquid of mass dm. So what is the amount of heat absorbed by dm mass of liquid to convert to vapor? It is L into dm, which we have said that it is delta Q. Therefore delta Q is equal to L into dm. Okay, so we have dm mass of liquid converted to vapor of same mass dm by absorbing delta Q amount of heat, and we have also said that L is the latent heat of evaporation per unit mass. Okay, so unit mass of liquid will absorb L amount of heat to convert to vapor. So dm mass of liquid will convert a heat of L into dm to convert to vapor. Therefore delta Q is equal to L into dm. Okay, so suppose this is equation 2.